So I think we should start to make sure we keep up with the schedule. So our first speaker is our first keynote speaker is Professor Rothschild. Professor Rothschild is a professor of material science and engineering at the Technion, Israel Institute of Technology. He studied physics and materials engineering at the Technion, and he did his PhD on metal oxide gas sensors. He spent 3 years postdoc at MIT, after which he returned to the Technion as a faculty member, and currently is the head of the Electrochemical Materials and Devices Research Group. His research focuses on electrochemical and photoelectrochemical materials and devices for water splitting. Professor Rothschild is also a co-founder of H2Pro, a startup company that develops water splitting technology for low-cost production. He was a member of several European consortia and had an ERC consolidated grant on photoelectrochemical water splitting. And finally, Professor Rothschild is also a recipient and winner of various prizes and honors. Okay, it's all yours.
Thank you, Gil, for the introduction. So I'm going to use the time to tell you a little bit about our work on decoupled water splitting for green hydrogen production. And let's start with a brief motivation. So green hydrogen is hydrogen produced from renewable sources, so from water, by a process called water electrolysis that you can see down here. And this process needs electricity. The electricity should also come from renewable sources such as wind, solar, etc. And the uses of such green hydrogens are tremendous. First of all, you can store the hydrogen, and that is a medium for renewable energy storage, together with batteries, which is kind of short-term storage, but seasonal storage would go, batteries will not do the work, so you need the hydrogen for that. And there is a whole platform, alternative things you can do with the hydrogen, such as fuel for transportation and feedstock for chemical production, such as ammonia, metal refining, petrochemical industry, etc. So projections or estimations say that in the future zero carbon energy landscape, green hydrogen would take something between 10 to 20% of the total amount of energy used by mankind. And in order to get green hydrogen, we should do this water electrolysis. So next slide, I spent a few moments to give you kind of state of the art in water electrolysis. So water electrolysis is this process, okay? So we break the bonds between oxygen and hydrogen in the water molecules, and we get oxygen and hydrogen. This occurs in an electrolytic cell with 2 electrodes, a cathode that produces hydrogen according to this reaction. That is called the hydrogen evolution reaction, and that is the standard potential for this reaction. And an anode that does the oxidation reaction, water oxidation or oxygen evolution reaction, that occurs according to this reaction with a standard potential of 1.23 volt. But as it happens, there are over potentials, and therefore you need to spend more than the minimum voltage, which is 1.23 volt. And that's how we define the efficiencies. Specifically in electrolysis, we refer to the overall energy efficiency that goes by the higher heating value of oxygen, which means if you burn the hydrogen and count how many calories you get, this gives you the equivalent of nearly 1.5 volt per electron spent in the reaction. And that's how we define efficiency. Why I mention efficiency? Because as you can understand, water electrolysis is energy intensive technology that consumes a lot of electricity. And since we have substantial energy losses, that's a major factor. And today, state-of-the-art electrolyzers operate like the champion one under really ideal conditions, which mean low production would give you about 80% efficiency, but typically we speak about below 75%, which means that you need to spend maybe 25 or 20 to 25 more electricity than what you really would like to spend in the ideal case. So that is one major obstacle for this technology. The other one has to do with this cell construction, which is shown by a picture here and by a schematic here. So the electrolysis system is a stack of bipolar cells, and this is schematics of one of these bipolar cells where you have a membrane with electrodes and current collectors that are stacked into a multiple bipolar plate configuration that goes like this. And as you can see here in the picture, only this part is actually the part that does the electrochemistry, okay? So here you have the membrane with the 2 electrodes on both sides. So the electrochemistry occurs here. But you can see that for the cell, you need a lot of sealing material in order to prevent the mixture of oxygen and hydrogen. And that is a major problem in scaling up the technology, because actually for the membrane and the sealing, you pay more than what you pay for the electrochemistry, for the electrochemically active parts. So I call this coupled water splitting, because in this conventional technology, the oxygen evolution reaction that occurs at the anode and the hydrogen evolution reaction occurring at the cathode occurs simultaneously in the same cell, and you must use a membrane to separate the gases, and you must use sealing in order to prevent the mixture through the system. So these are the major problems we have that essentially translate into high hydrogen production cost, which cannot compete with alternative ways of producing hydrogen, such as we call this black or gray hydrogen produced from carbon or from natural gas. The idea is we would like to produce hydrogen without CO2 emission, and for this you need to go with water. And currently the technology is limited in efficiency and in membrane cell construction. So we come with an alternative approach to this problem that dates back to about 5 or 6 years ago, when I was working on photoelectrochemical water splitting, which is essentially combining electrolysis with photoelectrolysis, or with the photovoltaic phenomenon, that basically you replace one of the electrodes. Instead of having a metallic electrode, you replace it with a semiconductor electrode, and you take advantage of the photovoltage created in the semiconductor by absorbing light and creating electron hole pairs. So schematically, this would be the cell construction, similar to what I showed in the previous slide. The only difference is you replace the metallic anode with the semiconducting photoanode that does all this photoelectrochemical reaction. And I'd like to point your attention to the fact that you still need to separate with the membrane these 2 cell compartments into the anode compartment that evolve oxygen and the hydrogen compartment that evolve hydrogen. Now, speaking about scaling up this technology, that creates a major problem, because if you look at solar fields, they comprise of millions of individual cells, typically 10 by 10 centimeters. When it comes to photovoltaic cell, it's very easy to collect the output from each and every one of the cells. It's simply you use the metallic buses to collect the electricity. Now the cell produces oxygen and hydrogen. You need to collect the hydrogen from these millions of cells, and just speak about the gas piping system that is necessary for it. This is a tremendous obstacle. And actually the gas piping system would cost you more than twice as much as you can afford for the entire system. So that's a big no-no. And several years ago, I had an idea, since I was working at the photoanode. So these are the electrodes that produce only oxygen. I had some thought that, okay, maybe we can somehow divide the cells into 2 components. One component would generate only oxygen, and then I can have a solar cell that produces oxygen and emit the oxygen to the atmosphere. And the other part, the part that produces hydrogen, maybe I can find a way to do it in a centralized fashion. So to collect all the cathodes from all these millions of cells and put them together in a big reactor that produces hydrogen. So schematically, this is shown here. And that, of course, would solve the problem of the gas collection from these millions of cells in the solar field. So that was the idea. And we found a solution for this, perhaps not ideal solution, but a solution. And the solution goes like this. So if this is the scheme of the conventional electrolyzer, again, cathode producing hydrogen, anode producing oxygen, and a membrane to separate them, we divide the cell into 2 compartments. So one compartment, or now it becomes one individual cell, produces only hydrogen. The other one produces only oxygen. And you can separate them over many meters if you wish, because they are connected only by electrical cables. The point is you need to make a way for the ions, in this case hydroxide ion, to transfer from the cathode to the anode. Otherwise, you will not complete the reaction. The way we do it is introducing additional 2 electrodes. We call them auxiliary electrodes. They're made of the redox system nickel hydroxide, oxyhydroxide. So that's nickel hydroxide. You can charge it and convert it into nickel oxyhydroxide. And then, so this is the reaction that occurs at one of the electrode. The electrode in the hydrogen cell is getting charged, while the counter electrode at the oxygen cell is getting discharged. So you have a limited capacity, you can charge until the capacity is over, and then you have to swap them between one cell to another. And that enables you to separate the cells over distance of meters in order to make the vision that I showed in the previous slide come true. So just to show you how it works. Okay, never mind. In the interest of time, I will skip this. It turns out that this auxiliary electrode that can do this work of transferring the ions from one cell to another are made of a very benign material, the nickel hydroxide, oxyhydroxide. That's the material we use in alkaline batteries, rechargeable alkaline batteries such as nickel metal hydride, nickel cadmium, etc. So that was the concept we introduced about 4 years ago. And last year we showed an actual photoelectrochemical system with a separated photoelectrochemical cell that produces oxygen and a separated electrolytic cell that produces only hydrogen, and demonstrated overall water splitting by sunlight over several hours with a system that goes like this, that you can split them over distance of meters. So that was how we got into working with these decoupled water splitting systems. But then we found out, actually Abigail found out while doing this measurement, a very interesting phenomenon. She noticed that there is a process of self-discharge. So how she noticed this? When she did the experiments during the weekdays, she always had repeatable conditions. But when over the weekend, she noticed that she cannot charge as much as she could charge during the week. And then we understood there is some spontaneous discharge of the charged electrode. And indeed, we dig out in the literature and find that that's very well known in the battery world, a phenomena called self-discharge of the charged nickel oxyhydroxide. It has a spontaneous chemical reaction with water that produces oxygen. And the point is, this reaction occurs very, very slowly at ambient temperature, but you can accelerate it by heating. So now we have a handle to control oxygen evolution at high temperature, and we can shut down this path by keeping the system at low temperature, at ambient temperature. And with this led to the idea of what we call ETAC water splitting. ETAC stands for electrochemical. That is the stage where we produce hydrogen. And then thermally activated chemical, that's the stage where we produce oxygen. So it's a two-stage process where first we put electricity between a cathode and a nickel hydroxide anode, such that the cathode produces hydrogen and the anode doesn't produce oxygen. Instead, it is being charged from nickel hydroxide to nickel oxyhydroxide. So we do that as long as we have capacity before this electrode would start to evolve oxygen. Then we stop the system. We switch the electrolyte from low temperature electrolyte to a high temperature electrolyte. So from ambient temperature to near boiling point temperature electrolyte. And then there is very fast reaction, spontaneous reaction that involves oxygen. So with this, we get two advantages. One, there is no membrane here, okay? We decouple the oxygen evolution reaction over the time. So part of the time, the cell produces only hydrogen, other part produces only oxygen. The other thing is this reaction produces oxygen by a chemical reaction that I will show later, okay? In fact, there are two electrochemical reactions occurring together at this electrode. But the point is that instead of producing oxygen with 4 electrons per one site, now there is 4 electrons per 4 sites. So essentially, this is a 1 electron reaction. Instead of having 4 electron reaction, 4 electrons per site. Now you have 4 electrons per 4 sites, and that helps us reduce the huge overpotential loss that you have in the standard oxygen evolution reaction. So we gain efficiency and we gain simple cell construction without membranes. So just to show how this works, let's see. I think I need to disable this. Oops. Yes. So this is the first stage where we pass electricity between the cathode. In this case, this is a platinum, and you produce hydrogen without gas evolution at the anode. And here, this is the second stage where the anode is moved into high temperature electrolyte and produces oxygen spontaneously. So that is the concept at the lab scale. In real life, that is a scheme of the process without moving the electrode from cell to cell. Of course, this is, that's for lab proof of concept, but in reality, we do this in a multi-cell system where every cell is connected to 3 water or electrolyte reservoirs. One is kept at high temperature, and that is the oxygen-rich electrolyte. One is kept at low temperature, that is the hydrogen-rich electrolyte. And we also introduce an intermediate temperature electrolyte to wash the cells from one stage to the other. So this is kind of schematic of the system, where each and every one of the cells here goes through the cycle where, let's say, first we pass electricity, we fill the cell with the low temperature electrolyte, pass electricity, produce hydrogen. Then the hydrogen goes to this tank and is gas separated in this tank. Then we wash the cell with a medium temperature electrolyte and then fill it with a high temperature electrolyte where you get oxygen, and the oxygen is phase separated from here, and so on and so forth. So these are the schematics of our systems. It has advantages of simple cell construction and very high efficiency, near 95% efficiency at the cell level. And this mode of operation is very dynamic. So it can accommodate power fluctuation as the system needs to be in order to work with, let's say, solar electricity or wind electricity. There are also disadvantages of this process being a batch process with thermal swing as opposed to a continuous process in conventional electrolysis. And we deal with these problems at the system level. So essentially, we replace complexity at the cell level and more so at the electrode level with complexity at the system level. So there's a completely different game here. Now, to show you our proof of concept result, so here you see 10 cycles, and you can see that the anode potential during charging does not change, and it is kept on average at a low potential of about 1.4 volt, which enable us to do complete water splitting at a cell voltage. This is for 10 cycles of about 1.5 volt, which give us very high efficiency, that is nearly 99% efficiency based on the hydrogen evolution, on the higher heating value. And we can also increase the current density up to 200 milliamps per centimeter square. These results were made at a relatively low current density of 50 milliamps per meter square, but today we get the same result with higher current density approaching 200 milliamps per centimeter square, which is already in the level of alkaline electrolyzers. And here you can see cyclability. So these are 100 cycles. So you see that there is some change from the first to the 10th cycle because the system is just like breaking in, but then the next 90 cycles are completely reversible. And here you see after a while, when we do multiple cycles, they are completely reversible. At the company, they already tested many tens of thousands of cycles. So this reaction is totally reversible. Just coming back now to the advantages. So one advantage is the cell construction. I come back to this picture. So this is conventional electrolyzer. This is a large scale electrolyzer, a megawatt scale electrolyzer. You see it is made of these plates, of bipolar plates, where each and every one of the cells here look like this, where we propose a completely different architecture. Because we do not need to separate between the anode and cathode compartment, we can simply stack them one on top of the other and then roll them like you have in batteries. So we have electrode rolls, and we stack them like marshmallow on the stick and then put them into a cylinder that holds them together with electrolyte. So it's a completely different architecture that is very easy to scale, is very compact, save a lot of space, and make all these issues of sealing and membrane and leakage much, much easier to handle. It also gives you the possibility to do high pressure electrolysis, which is very difficult with this construction. So these are big advantages at the system level. And as I mentioned before, we have the advantage of the efficiency, very high advantage. We operate at 99% efficiency at the cell level, where other technologies operate at 75, maximum 80% efficiency at the cell level. That's a big advantage. To understand this, we need to look a little bit about the mechanism of conventional water electrolysis, which is basically follows 4 electrons per site. So here M is a metallic site at the surface that undergoes these 4 different steps In case of alkaline electrolysis, in each step, you add an hydroxide ion and extract. You add an hydroxide ion and extract an electron. Yes, so you change from different adsorbates, and ideally, you would like each and every one of these steps to consume 1.23 volt, and then you will have no overpotential loss. But as it happens, these steps are not identical. If they were identical, there would be no overpotential loss at zero current. But they are not identical. Some of the steps are easier than the others, which means that the other steps are more difficult, and the calculations or looking at hundreds of calculations for different electrolytic material calculation made by density functional theory show, so you put them here on a graph, show that the difference in the adsorption energy between the third and first adsorbate give you on average 3.2 electron volt instead of 2.4 electron volt. So this means that you have, this is the reason why you have the overpotential. That's not standard overpotential. It doesn't have to do with the kinetics of the reaction, but with thermodynamics of the reaction, because it's a multi-step reaction where different steps are not equal. And that is the main reason why we suffer from low efficiency in conventional electrolysis. And you can see that that's not only calculation, also the best electrolyzers, the best electrocatalytic material for oxygen evolution, they show that under a low current density, look, this is not high current density, that's 10 milliamps, you get an overpotential of 0.3 volts, which translates into this relatively low efficiency. So we do it differently. We do it in two stages. In the first stage, we charge nickel 2 to nickel 3. So we charge nickel hydroxide to nickel oxyhydroxide, where essentially we have to charge 4 sites in order to generate, in the next step, 1 oxygen. So instead of 4 electrons per 1 site, now we have 1 electron per 1 site reaction. And then in the second stage, which does not consume any electricity because it is a spontaneous chemical reaction, we evolve the oxygen molecule. Essentially, this is, although this is a chemical reaction, but essentially like any other kind of corrosion reaction, it comprises of a complementary anodic and cathodic reaction, where the anodic reaction would be exactly the opposite of the charging reaction. And you also have the OER. So I do not say that we replace the OER, but we do the OER in a different pathway that goes through 4 sites instead of 1 site. And that is what enables us to reduce the overpotential, the large overpotential loss that you have for normal electrolysis. And that is shown here. So, there are different pathways for oxygen evolution reaction. That's a slide from a review article that was published about 10 years ago. The conventional electrocatalytic material goes by this 4 electron per 1 site reaction that is shown schematically here, where we go with a different mechanism where we suppose, okay, we haven't proved this yet, but based on literature on this material of past research, we think that the mechanism involve 4 sites, which help you to divide the reaction over 4 sites, help you to reduce the overpotential. And there are different alternative pathways. Currently, we are looking into the different possibilities and trying to figure out what exactly is the reaction pathway in our system. So to show you now in real results, so this is the charging reaction that we do in the first step. So we charge nickel hydroxide to oxyhydroxide, and you can see that we do this at a lower potential than the potential where we can evolve oxygen, and that is essentially the energy we save. Yes. So about the reversibility of this reaction, so the reaction we do convert this beta nickel oxyhydroxide, which is the layer structure, where in these interlayer spaces, you have hydrogen pointing out of every oxygen atom. That's the nickel hydroxide. And in the nickel oxyhydroxide, we extract half of this hydrogen, we extract it out of the system. So that is a reversible reaction that consumes half of these protons, go out and combine with the hydroxide ion at the surface of the electrode to produce water. And this reaction has nearly 0 volume change. So you see between these 2 phases, they have nearly identical structure, except for this hydrogen occupancy. with nearly zero volume change, and that allows this reaction to be cyclable over tens of thousands of cycles. And indeed, this material has been used in space, batteries that go to space, such as the batteries that go with the Hubble telescope that needs to service many, many years, are based on it's called the nickel hydrogen battery, which essentially does the same electrochemistry, but without oxygen evolution. So that's the reason why we choose this material, because of its long cycle life. So just a few words about the electrode themselves. So at the beginning, we did the electrode made of composite structure with carbon for electricity, for conductivity, and nickel hydroxide microscopic particles. And indeed, we got reasonable results, but with relatively low rechargeable capacity. And then we changed into this porous electrode, where we started with the porous support, macroporous support by nickel foam, onto which we deposited this about 10 micron nano structured layer of nickel hydroxide produced by electrochemical deposition that give you a fine structure that you can see here that support very effective mass and charge transport from the electrolyte into the electrode. And with this, we were able to increase the, we call it the regenerated charge. The regenerated charge is how much charge we can put in the system in the electrochemical stage and then extract it completely in the chemical stage. So you see that with the pasted electrode, we got about 1 for a half-hour charging. But in case of the electrode deposited electrode, we got nearly 3 times more. Today, we get even much higher results. And that is because of this fine structure that support the effective mass transport. But still, we have an issue with material utilization. We don't use all the deposited material. In my lab, we use about 5%. So we have material utilization, relatively low material utilization. At the company, they do much better. They already get about 20%, and the goal is to increase it by a factor of 2. And then we would be, this would enable us increase the cycle time. So instead of, let's say, 15-minute cycle, we can go into half-hour cycles, which is very advantageous for the operation.
Avner, just we are already 8 minutes past the time. So if you...
Yeah, so that's the last slide. Okay, so now we also switch from nickel foam into carbon electrode, and there is a lot of things going on. And that's bring me to the summary, which I think because I'm overdue, I would skip. So essentially, we replace conventional electrolysis by a 2-step process without membrane, with high efficiency, and that's a major advantage. And yeah, thanks to my partners. So the discovery was made by Avigail and Chen and my partner, Gidi Greder, my group and the company. And I think now I will let some time for questions if Gil allows.
Okay, thank you very much for this very interesting talk. We don't have much time for questions, so maybe just one quick question for Professor Rothschild. Okay, so because of lack of time, I would like actually to ask something, but because of lack of time, I would like to thank you again for this very interesting talk. And we'll move to our next keynote speaker, Professor Nir Tesler. Nir Tesler is a professor of electrical engineering and is the Barbara and Norman Seiden Chair. He's currently the head of the Microelectronics and Nanoelectronics Centers of the Technion. He did his studies with the Department of Electrical Engineering in the Technion in Israel, after which he held a researcher position in Cambridge in the Cavendish Laboratory. And in 1999, he returned back to the Technion as a senior faculty member. Professor Tesler is also the CTO and co-founder of several startup companies, such as Spintronics and Carbon Valley Technologies. And he's also a recipient of various awards and honors. Okay, Nir, please.
Thank you, Gil. Hope you can see my slides.
We can.
Thanks. All those startups are long gone, but thanks.
I wasn't sure about that, so okay.
Yeah. So today I'll talk about a methodology that we've developed, which we call device synthesis. And that's like a method to try and design devices that could help us overcome challenges that are introduced by materials, new materials. So basically what we are looking at is trying to get out of the common approach that we all know that the devices that many of us are using or trying to develop, the devices themselves has been around for ages, like the gallium arsenide or silicon. And now if we are going to use what we call third generation materials, then it's obvious that if something doesn't work, it's the chemist. And because the materials that do not perform the way they should, for some reason, we all tend to forget that the devices that survived as useful for silicon are those who were matched to silicon. So maybe it's worth going back and rethinking the devices. And that's really our methodology. So really what we are saying is that we should call the device engineers to the rescue and not just leave it all for the chemist, because the materials are never perfect. And really what we have developed over the years is a method that has two building blocks. The one is the knowledge base that we have to develop, and it is composed of many just a sec. It is composed of many parts, but really everyone or every project will have its own part. These are the ones that we have developed within the group, but these are not the only ones. And once you feel that you know everything in the context of devices, you can try and produce a challenge that you want to overcome, the limiting factors that many of them are to do with the materials at hand. And then you need to find somehow a way to come up with a new device structure. And it's written here, simulation or inspiration, and really both work. And luckily, we have to do a cycle between the two. So there is quite a challenging of going back and forth, making sure that the simulation or the new design really works, and you need to analyze it and find out why it doesn't work. But if you have enough experience and knowledge, then it can be done. And luckily, we don't need to do everything ourselves because there are lots of other people out there. So building the physical picture or the material or knowledge base is largely reading loads of papers. So really just to put something really behind this concept, I thought I'll talk about the solar cells, which match the theme of energy. So for example, a long time ago, the couple P3HT PCBM was the working horse. And we know that there are lots of mechanisms that take place. Here is the structure of the solar cell, and we have this, what we call bulk heterojunction. One color is the P3HT, the other color is the PCBM. And when we shine light into it, then what we have is generate excitons. These excitons would diffuse to the interface, and they will create a charge transfer excitons. And hopefully these would split into charges, which we call free charges, that would then drift and diffuse to the electrodes to produce current. This is like the ideal case, but ideality is only in the textbooks sometimes. And really we have the loss mechanism. We have the trivial one that there is always light emission accompanying absorption. We have charge recombination. Although we split them, they may find each other again and recombine. And there are some unique processes that are found in organics more than in inorganics, which we call the charge exciton annihilation. And there are loads of other processes that are not shown here, but this is really the essence. And the main thing is that is to try and filter out or synthesize the processes that we can tackle by designing a new device. And when we say design a new device to tackle the physical problems, we really looking at the layers to choose, how to control the interfaces, what contact to use, and how to lay out the materials in the device structure itself. So this is still abstract, and we've really been through this abstract stage for a long time, building up the knowledge base. With two key people were Noam, who started it all, and Lior, who took us a long way in the context of P3HT, PCBM. And from this long journey, we managed to find out that the open circuit voltage of solar cells is really limited by the built-in potential. And this is something that turned out to be very surprising, because the one thing people always like to say that is excellent about organic materials is that there is no such thing like a Fermi level pinning, but there is in any organic materials or in any semiconductor. And it is also very hard to decipher that this is what is killing your device open circuit, because it just introduces another loss mechanism. So many people ignore it, and some still try to deny that it exists. Recently, I mean, last week, I think there's a paper that published that we can think of it as an excuse to what we are doing. And really, they looked at different technologies and trying to look what are the relevant losses for each technology. You can see here the organic PV, but there is also SIGs, perovskite, silicon, gallium arsenide. And of course, the gallium arsenide are the most efficient. But what's important for us here is to notice that what we were looking at first is this loss mechanism, the open circuit. And we realized that it's limited by the built-in potential. So really, this was when we first really implemented in the context of solar cells, this cycle, they're going towards trying to find a solution, how to enhance the built-in potential, but using the same absorber, not really enhancing the band gap of the absorber. And we managed to come up with a device that while we did the simulations that can be found in the two papers below, you can see that we plugged in the properties of P3HT and PCBM, and we managed to get a really nice enhancement in the open circuit voltage. And the interesting thing about it is that the device structure, or the energy level diagram that we came up with, is not intuitive at all. You see, here is this one electrode, here is the other electrode, and the charges that we generate are supposed to go out, and looks like there is a barrier for extraction. But for some reason, you can gain a lot here. And why we gain a lot is because we enhance the built-in potential. So I placed here the two structures. We know that the electrodes are pinned relative to the band, so I kept the pinning relative to the edge of the band similar for both contacts. But because we have this change in the energy level diagram, like what I mentioned as the barrier for extraction, we can gain a higher built-in potential, which is the distance between the electrodes. So really, if you put them all one next to the other, you immediately see that we have a higher built-in potential, and that allows us to enhance the open circuit voltage in this kind of devices. And just for intuition, this kind of change in the band structure is like a layer dipole, which is like interface dipole, only it takes more space, it's longer. And we needed this to decouple the Fermi level pinning mechanism. We don't want the metal to directly talk with the absorbing material. And not long ago, this was really demonstrated in a collaboration we have with a group in Dresden that showed that it's a way to enhance perovskite solar cells. So this was one way of using this methodology. And then P3HT PCBM was gone, and we have the non-fullerene acceptors. And it seemed that we had this magic material, then the open circuit voltage is not a problem anymore. And then Dan started to look carefully into the physical mechanism. And we see that charge separation extraction becomes an issue. And it meant that we have to think differently or enhance the photoconduction efficiency, the power conversion efficiency, sorry. And his study was really to look at what's unique about organic semiconductors is that we generate bound pairs. And really what we would like to do is to make sure that within the device, they separate into 3 charges. And we all know that one of the things that's working against us is the Coulomb binding between them. And the challenge was how to really look into the physics properly in the context of organic devices while taking into account some of the confusing parts of the role of energy disorder and entropy. And I have a few slides here on the physics, which I'll go quickly through because of the lack of time. And this is really just a slide for those of you who are not really into entropy, is really just to demonstrate that if we think that separating the charges have only one path, that we can go only into one direction, in real life we can go into many different directions to separate the pairs. So really if we had only one rate, now we have loads of different possibilities. And if we sum them up, we can come up with an effective rate that has the binding energy minus the sum of the contribution, because we have many options. And this is really what we call entropy. This is really hand waving just for this case. And all this is known when we know that the binding energy is effectively reduced. And the biggest problem was that everything is known. You know, entropy is not new, disorder is not new. The only challenge was how is the device reacting? How can we get the data for the device? Or in other words, we have the disorder. There are different places with different energies, and how do we average between them? And really, this is what the challenge was, how to average. And the idea was to look through the device's eye. I apologize for doing it quickly. And really, the unique thing, besides doing all the physics properly, is the unique contribution from Dan's work was really finding the effective binding energy for the eyes of the device. And this is really critical if you're going to design devices. You need really to look at how the device filters out the physics. And really what is important for us, we're looking for charge generation. So every environment has a dissociation efficiency or charge generation efficiency. So really what the device measures is the total charge generation. So if you want to average and find the effective binding energy, you need to average across the dissociation efficiency of every point in space. And this looks like a minor issue, but it's critical because that's the only reason that Dan managed to show that when he measures devices prepared by our colleagues in the US, he managed to put his model directly on the measurements that he did in our lab using their devices. And this is not an easy thing to do, to get this kind of a model to fit something that is measured from a device prepared elsewhere. And this really changed our focus on this idea and all these studies, that you look again at this new paper and you see that there's not just one color here, there are lots of different losses. So really the approach to look at is to try and maximum the power extraction. So looking only at this short circuit current, VOC or fill factor separately doesn't always help you find the right solution. And really we focused on that point, and this is where Himanshu came into the game. And he managed to introduce a new device structure, which is demonstrated here for a bilayer device. And really what we have, you can read it in this paper, but what he introduced through modulation doping, something that looks like a dipole again. But the important thing here is just look at the slope of the bands at the junction. And really this is the secret of this new design. We enhance the internal electric field at the junction at the maximum power point. So we enhance the charge extraction, and this way he managed to demonstrate a really large enhancement in the performance. So really this is a summary of what I've talked about. Sorry for being a bit quick. And really the first part or the first structure, we really were aiming to suppress the recombination at the contacts. That's why the built-in potential was the problem. And the second approach was to really enhance the charge separation, because no matter what you'll do, there will always be some kind of binding energy in this type of materials. And really this means that you have to look at things from a slightly different perspective. And the only way we managed to get to this new perspective is through this methodology where we look at the physics through the eyes of the device. And at the moment, Hella in our group is trying to produce something which is a bit more universal than what Himanshu managed to achieve. And I'd like to end by thanking you and the funding by the ISF and the Ministry of Science. Thank you.
Thank you very much. Question for our keynote speaker. We don't have much time, so maybe a single fast question would be nice.
By the way, if you're interested, we have a YouTube channel. It is called OMD YouTube. You can find the lots on there.
Okay. So I'll just ask a very quick question. So what you show, the second development that you presented, this is something that is very generic, I understand. This wasn't a material specific. This was a general approach for VOC enhancement.
Yeah, I mean, the two things we did, it was general. I mean, we came up, the first one, we designed it for OPV, but it was first demonstrated for perovskite solar cells. Mm-hmm. And the second one is general. There are lots of third generation devices that suffer from charge separation. We found them having a clear binding energy. They're getting charges out of the active region is a major problem for many technologies.
Right. Efficient membrane collection, I guess, right? Efficient contact.
Yeah. If you want to link it to Avner's talk, yes, definitely.
Right. Okay, thank you very much, Nir, for this very interesting talk. And we'll move to our next invited speaker, Professor Rafi Shikler. Professor Shikler is with the Department of Electrical Engineering in Ben-Gurion University. He has a bachelor degree in physics and bachelor degree in mathematics, both from Tel Aviv. He did his master at the Weizmann Institute. And then he came back for his PhD at Tel Aviv University. Afterward, he spent his postdoc position at the University of Cambridge, at the Cavendish Laboratories, and after which he returned as a senior faculty member to Ben-Gurion for the Electrical Engineering School of Electrical and Computer Engineering. Okay, Rafi, please.
Thank you, Gil. I hope everyone hears me. I will look at a different aspect of what Nir said of device synthesis, and I would look on the role of transparent anode in organic devices. In most devices, as you know, if you talk about electronics, then we have an active layer and we have the contacts, the cathode and the anode. And in OPV and OLED, the anode is usually one of them, at least, is transparent. And I will look at the anode, the transparent anode, and I will focus on the interface of it with the active layer. first we will talk a bit why do we need transparent anodes and what the implication, and then we'll go into two major effects. One is a power loss, which is quite straightforward. The other one, which is also interesting, is charge injection and collection at the interface. And in that, we have reformulated the idea of Schottky contact. So in most organic materials, we have low mobility and high disorder. As you can see, Nir talked about P2H2, but it's relevant to almost all organic materials. The mobility is rather low compared to silicon. And therefore, we have a short carrier diffusion lake inside an organic layer, which also lead to an anode in this case that should cover the entire area of the cell. And if the anode should cover the entire area, that means that the anode must be transparent. And obviously, if it's transparent, it's not as good a conductor as a metal. And we have studied two aspects of it. The first one is straightforward, is that because it has inferior conductivity to metals, obviously it leads to power loss. This is an ongoing work for many years before us, and there are ideas how to overcome that. But we managed to develop a simulation methodology that can help predict from point of view of planning what is expected. The other thing is that the anode is not just have poor conductivity, it is a dielectric, and as such it has different permittivity than metal, and this will lead to low injection current at the dielectric interface. So if we have a metal, then metal compared to a metal dielectric interface has a much higher injection current than a dielectric. So I will cover both of these. And the first one was how to simulate a transparent anode. The idea is that we solve the two-dimensional Laplace equation inside the anode. And the cathode in our case was made of aluminum, so there was no issue in trying to solve anything there because we can assume that the voltage there is constant. And then we need to couple what we have in the anode, which is one dielectric, to what we have in the active layer, which is a different dielectric, and therefore we have to modify the boundary conditions at the solar cells. And this can do in two different ways. One which we will cover here, and the other one I will add to it at the second half of the talk. So what basically we have done is that when we have an anode, we have a connection to the collection of an organic photovoltaic at one point. There are two sides of the anodes that you can assume that the electric field is zero. And the other, the last side, which is the fourth one, you have to have something which connected to the active layer. What we choose as the boundary condition is the current, because in the interface between them, we have a current that comes from the active layer. And to translate that into a boundary condition on the Laplace equation, we just use Ohm law, and therefore we can translate the current into a boundary condition on the electric field. Then we have a well-defined Laplace equation, which can be solved. From that, we can calculate the distribution of the electric, of the potential L dielectric field within the anode, and use that as a boundary condition for the active layer itself. And you go back and forth until you get something which converges. So what one can observe is that when you look at the current flow, since the anode has a finite resistivity, what you will get is that there is a voltage development across the anode. As you go further and further from the point that the current is collected, you will get that there is a higher voltage. And therefore, this implies that at this point, the cell feels a bias which become closer and closer to the open circuit condition. And if you get further enough from the collecting contact, then what you will get is that your system goes into open circuit, and there is no point in adding more and more size, increasing the size of the device, because it won't improve any charge collection. If you will look at it from the point of view of how the voltage is developed, then you can see that in a P2H2 PCBM system, when you are at very short side, something about 1 millimeter, and then you will have most of the current is the same, and you will get that you get the same short circuit current all over. When you increase the device size a bit, you will get, obviously, there is a larger and larger development of voltage. And when you will get to devices which are longer than 1 centimeter, you can see that the voltage development across the device is saturated. And obviously, at this section, we have a long cell that doesn't really contribute to the current. You can then go to the maximum power point, try to calculate that, and you can see that as you increase the cell size, at the beginning, you have a large increase in the short circuit current, and this start to saturate as you go to higher and higher current. And also in the maximum power point, you can see that we just track it, and it also start to be less efficient to increase it. And just to prove that we don't just do simulation, but also measure things, when you do this calculation and do really fabricate cell, then you can see that when you have a small cell, relatively small cell, you have a current, you increase the cell size, then the current jumps, the current really jump. And when you start to increase it further and further, then the jump in the currents becomes smaller and smaller. Now, this is not new, only the calculation idea was new. And what we then do is we wanted to add a metal grid in order to improve the conductivity and the collection, sorry. Now, when you add the metal grid, one thing that you should ask yourself is where do you would like to put these metal grids? And in our model, we can just introduce this point as collection points where they have a voltage which is equal to 0, and therefore they are situated at the short circuit currents. Now, if we have no grid lines, then what you will get is that you have a saturation in the voltage. If you have one point and you put it smartly across your device, then you can see that you reduce the voltage development across the anode, and therefore you increase the charge collection of the device and also the efficiency. If you add more and more points, at some point you will see that you will almost flatten the voltage distribution. Again, the question is where to put these grid lines. And what we found out is that if you have one grid line, let's look at this example. The grid line is positioned at 0.5 millimeter. Then basically you have a division of the entire 10 millimeters into 3 cells. One between 0 and 2.5, one between 2.5 and 5, and one from 5 till the end. And the first 2 cells are symmetric, while the third one is obviously, since it's larger, you have a larger development of voltage on it. And this is what gives you the idea of how you can divide the cell if you really like to achieve maximum point. If you have just one line, you can put it everywhere you would like across the anode. The maximum will be at 2/3. And this was valid both experimentally and obviously from the simulation. And just to give you the intuition, the idea is that if this point, the grid line point is very, very close to the main collection point, then you have a large area with no contribution to it. If you go to the other extreme, then the area from this point to the major collection also will be a large area with minimal contribution, and therefore the best way is somewhere to position it at 2/3, that you will have equal distribution of voltage, of maximum voltage between these 3 cells. We didn't manage to prove that mathematically, but at least experimentally it works. Now to the second thing. What happened at the dielectric interface? And here we also went to the equation that people are using for describing charge injection and collection into the device. And these equations are usually attributed to Scott and Moliares and are based on a modification of charge injection at a Schottky contact. Now, what people are doing is that it is assumed that the injection current is proportional to the potential barrier at the interface. And more than that, you have to overcome that, and what helps you to overcome that is what we call the image potential, that when an electron getting close to the interface, it creates an image potential, and that image potential reduces the barrier for injection. And when you have a metal surface, this is easy thing to say, and you can really calculate that straightforward. It's also easy to calculate in a dielectric, but with metal, it's even nicer. And this is what you have in the Schottky formulas. And the equations are very simple. Nothing new here, and you will get that the image potential is just Q star, which is the ratio between the two charges, and times Q square over 16 pi and the distance. Now, in metal, this Q star is 1. However, in the electric, this is not true. For example, in ITO, what you have is that this dielectric is 3. If you go to P dot, then it's 3.9. So what is the implication of that? If you try to look at the interface between this electrode, let's say of ITO and the organic layer, then you need this Q star, and Q star can be calculated by just using simple electrostatic to be equal to epsilon 1, which is at the electrode side, minus epsilon 2 divided by the sum of them. So instead of having Q star equal 1 in metal, you go down to 0.5 in ITO, which means that the reduction in the barrier is smaller. And if you use instead of ITO, P.PSS as an interface, you will see that this is supposed to reduce it even further. So instead of having a low barrier, you will have a much higher barrier for injection. It doesn't have to be much, but depends obviously on the choosing of the material. And if you just look on what we did as a simulation, you can see that there is an expected difference of about ×2 between the current density when you have a Q star of a metal and when you have a Q star of an ITO. And then we went and we didn't want to involve also 2 types of carriers inside like we have in the solar cell, but we wanted to focus on just 1 type of carrier. So we introduce NPB between 2 metal layer of gold and between P.PSS and organic layer, the organic layer and the gold. And as you can see, there is a difference between the expected current and between these 2 stages, these two type of contacts. And our results fit quite nicely, not on the low voltage regime, but when you go to voltage of around 3 volt and higher, then they fit quite nicely with the experiment. And I think that this is summarized here when we develop a 2D simulation which unite both transparent anode and organic layer. We can study the effect, the rule of the finite conductivity. We also modify then the boundary condition for the charges due to the changes in the potential, which is also attributed to that, and you can see how this works. And we also did some optimization for grid shape and positioning. Thank you.
Okay, thank you very much, Rafi. Questions for our speaker? We don't have much time. So I have a quick one. So basically the formulation that you did for ITO, this will be also valid for?
ITO, yes. We measure it for P.PSS. So it can be for any kind of a dielectric electrode.
But not only the electric, also the active material. It could be silicon. You still have the same problem?
Yes. You will have something different, yes, obviously. You can take it even to extreme, just put water. You will get Q star, which is negative.
I see. That's really extreme. Last question for Rafi. Okay, Rafi, thank you very much. And our next speaker is Gidon. Can you upload your, share your, okay. So Gidon is a faculty member, senior faculty member with the School of Electrical Engineering at Tel Aviv University. He obtained his degrees, his education in Tel Aviv University with the electrical engineering department. He spent several postdocs in Tel Aviv, in Technion, and several years with the Joint Center for Artificial Photosynthesis in the Lawrence Berkeley National Lab. And now he's a senior member with electrical engineering in Tel Aviv. Please, Gideon.
Okay, great. Thanks a lot for having me here. It's a pleasure. And it's kind of nice because I think that this talk actually connects really well with stuff that was already discussed, especially the work that Neil presented. And the basic idea is that we are talking about the different solar cells with new materials or maybe new structures. And when you start working with them, they never operate so well right from the start. And in order to understand what's wrong, we need to map losses. And well, when you want to map losses, this is an essential part of optimizing devices. And when you think about how you want to map losses, you want to do this under relevant operating conditions. For example, not in vacuum and in cryogenic temperatures or whatever. You want to do this while the cell is operating on sun, for example. And you want to do this with very little assumptions on charge transport. We don't want to impose our own biases on what's going on. And to do this, we started working on something that we use the term for spatial collection efficiency. This is something we started back in Avner's lab at Technion. It was, I think, 2015, more or less. And the idea is this: we use this term that we call the spatial collection efficiency, which is the fraction of carriers that are generated at a specific point that contribute to the current that you measure. For example, if we take this kind of solar cell that's say Pn plus made from a lost material, we can perhaps say that if carriers are generated near the PN junction, there's a chance for them to be separated and collected by the contacts. On the other hand, if minority carriers are generated further away, there's a higher chance that they'll recombine somewhere. So putting all this together, we can perhaps think of what will be the spatial collection efficiency profile for this kind of device. It will be probably lower in the highly doped regions that get to some high value near the PN junction and decay as you go deeper into the device according to the diffusion length, something that looks pretty much like what we have here. To put this in terms of math, we can say that the current that we measure is an integral over the optical generation multiplied by the spatial collection efficiency, the probability that this optical generation event will generate current. So by solving this equation, we can actually extract this profile and basically get some pretty deep understanding of what's going on in terms of collection inside the device. The difficulty is that there are infinite number of solutions to this equation, so we need to get more information on the system. The way for us to do this is to measure quantum efficiency, or IPC, depending on where you come from. You can give this a different term. Essentially, you measure the current as a function of the incident wavelength. Now, for every incident wavelength, you have a different integral that lets you have more information on the system, so you can more easily perhaps converge onto the physical solution for the spatial collection efficiency. So just to sum this up, the spatial collection efficiency can be thought of as depth profile for charge collection and loss in the device. And the way we find it is we use optical modeling to find the optical generation at every point for every incident wavelength. We take PQE measurement or IPC, same thing, and throw this into a numerical algorithm that will spit out the spatial collection efficiency. So this is something that we already did several times on several different material systems, and we're able to get pretty interesting results. For example, we can extract, this is fairly trivial, the diffusion length in silicon solar cell. We were able to discriminate between bulk and surface losses. This was in CVO photo anodes for water splitting. discriminate between slow reaction kinetics due to imperfect chemistry and fast recombination events at surfaces also in CVO. And one of the more interesting results was the finding that in several metal oxides, this year specifically for hematite, not every absorbed photon generates a mobile charge carrier, and we can actually quantify the probability to generate a mobile charge carrier according to the wavelength of the incident photon. And it was quite interesting that this probability is very far from one for a big chunk of the solar spectrum. So all in all, for the spatial collection efficiency can tell us quite a lot about things that's happening inside solar cells and photoelectrochemicals and so on. But all the stuff that we see here, all this information we gain from looking at currents. And as already discussed here, currents are just a small part of the entire picture. The other part of the picture that we must address is what's happening in terms of voltage. And this is understanding how to map contribution to photovoltage. This is what we're going to talk about now in the second part of this talk. The way that we tackle understanding contribution to photovoltage is actually passing through luminescence and external luminescence efficiency, or the photoluminescence quantum yield. There are tons of different names for this. The idea is it's the fraction of photons that are re-emitted in photoluminescence out of the device, and it was shown that the open circuit voltage is tightly connected to this number. The reason is that photovoltage is determined by quasi-Fermi level separation, but also radiative recombination. So these guys are tightly coupled, and actually can calculate equivalent to the Shockley-Kaiser limit that is reduced as you reduce the photoluminescence quantum yield or the external luminescence efficiency of the device. So perhaps if we can map the contribution to the external luminescence efficiency, this can tell us something about the contribution to photovoltage. And maybe we can map photovoltage buildup in the device using this kind of mechanism. Taking a step back and see how this whole is put together. We talked about spatial collection efficiency. It was the fraction of carriers that are generated at some point they contribute to current. We are looking at a particle flux that is a result of the optical generation and the probability to contribute to this particle flux. So I can just perhaps replace the particle flux instead of electrons. I'm going to look at photon flux out of that device and do the exact same thing. I can look at the probability for an optical generation at some point to contribute to photoluminescence. And this is what we call the spatial external luminescence efficiency, SELE. So again, by looking at photoluminescence quantum yield as a function of the incident wavelength, we can extract the SELE and maybe get some understanding of the photovoltage. But this is not all. Maybe there's some other interesting aspects to this. So once again, a good solar cell is a good LED. So SELE can tell us about the contribution to photovoltage, but perhaps you can also measure both IPC and photoluminescence and now get some added value here to make some synergy by looking at these two together. So first of all, the spatial collection efficiency tells us about the contribution to current, the SELE about the contribution to voltage. So if we look at both of them, we can actually map the contribution to power generation inside the device. This is on one side. On the other side, well, if we look at all the different things that can happen to a charge carriers can be generated as current. Well, we map these with the spatial collection efficiency. They can recombine radiatively. We just talked about how we map these. Well, besides those, they can only recombine non-radiatively. So all in all, if we just can map 2 out of the 3, we can actually find the third. So by doing the SELE analysis and the spatial collection efficiency analysis, we can get a complete functional mapping of everything that's happening inside the device. So from this, we conclude that there's quite a strong motivation to look into this, and we set out to do this. This is an illustration of the setup that we use to measure the photoluminescence quantum yield as a function of the incident wavelength. We had a monochromator, and we collect the PL spectrum with an integrating sphere. And we started with the simplest system we could think of, which is just a gallium arsenide wafer. The output that we get, this is pretty much the raw data. These are photoluminescence spectra as a function of different incident wavelengths. It is already calibrated here, so by integrating each of the spectra, we can get the photoluminescence quantum yield, so which changes as so with respect to the incident wavelength. And now all that is left is to plug all these and with the optical generation profile into this equation and extract the spatial external luminescence efficiency. Before we do this, let's take half a minute to think about what we expect to see. So we have here a station from a gallium arsenide wafer, and this is where the surface is. And if carriers are generated some distance from the surface, there's a chance that they will recombine radiatively and emit a photon in the process that we call photoluminescence. However, if this optical generation is happening deeper inside the device, this radiative recombination photon can be reabsorbed somewhere inside the wafer, which is what we call self-absorption. And if the optical generation is happening very close to the surface, there's a higher chance for surface recombination. So once again, we will not measure PL in this case. So putting all this together, we expect that near the surface, the SCLE will be fairly low. It will increase as we move away from the surface and then decay as we move deeper and deeper inside the material. So we extracted the SLE out of the spectrum here, and as you can see, with the surface being at Z equals 0, we can see a very strong indication of surface recombination losses, the decay due to self-absorption, and actually the peak here can be the height of the peak can be attributed also to optical coupling, how easy it is for photons to be emitted from the device, and which might also be relevant for people working on LEDs and stuff like that, and also very important for solar cells as well. We can test that this profile actually is physical. One way to do this is to throw it back into the equation here and see that we can reproduce the incident wavelength dependent quantum yield, and as you can see, it works pretty well. So this is all was pretty reassuring, and then we are very happy with these results, but we're still missing some stuff. For example, how do we connect surface recombination velocity or bulk lifetime to terms that we have here? And if you want to do this, we have to do this. A good way to do this would be through simulation. I will not get into all the details of the simulation, but I'll just say that this is pretty complicated because you need to account both from diff diffusion and for photon recycling. The fact that you have a radiative recombination at one point and this photon will be absorbed somewhere else and so on. This is quite a mess, and we do this with an iterative process between coupling several simulators. But the nice thing about it is that with the simulator, we can actually calculate the spatial external luminescence efficiency directly, assuming specific optical generation profiles. So we can actually assume, for example, surface combination velocity and see how this will affect the SLE that we can extract. And this is what we see here. These are SLE profiles with the surface here at Z equals 0. And as it follows pretty much the same shape you've seen earlier, as N1, and as one would expect, we see that the SLE, the surface, is very sensitive to surface recombination. Each of these profiles is for different surface combination velocity, if I haven't said earlier. We can do the same by looking at different bulk lifetimes, and as one would expect, by increasing the bulk lifetime, you can increase the depth from which photons can be extracted from the device. So all in all, we have seen that we believe that spatial collection efficiency and spatial external luminescence efficiency can be very useful tools for device characterization. the extraction of the SLE was demonstrated experimentally on a gallium arsenide wafer, and we believe that this kind of analysis can help quantify a range of material processes and device processes like combination that is radiative, non-radiative, and contribution to the photo voltage. And we are now looking at applying this to a range of different material systems and devices. And with that, I would like to thank all the people who contributed here, the people from my group. And as I said earlier, this started in Avner's lab, actually the Technion, and continued also during my postdoc at LBL. So thank you very much, and I'll be happy to take questions.
Thank you very much, Gideon. Questions, please. We don't have much time. So I'll just ask a short technical question. So when you do the external luminescence, you manage to both in simulation, in calculations, and in experimental to collect all the photons from half a solid angle.
Okay, so in terms of experiment, we work with an integrating sphere, and right now, the cell is pretty flush. The material, the wafer, is pretty flush with the surface of the sphere. It's not inside. It's not at the center. It's at the surface, and the way to calibrate is with respect to a fully diffusive reflection standard. So, assuming that the cone, escape cone, or sorry, not the cone in which PL is similar to the scattered light of the standard, this is the range of the error that we have. In terms of simulation, it's much simpler.
Right.
Yeah.
Okay. Okay, Gideon, thank you very much.
Yeah, sure. My pleasure. Thank you.
And we'll proceed to our next speaker, Professor Igor Rakhinov. Professor Igor Rakhinov is a senior faculty member at the Department of Natural Science of the Open University of Israel. He obtained his bachelor in chemistry from Tel Aviv University, where he also earned his PhD in chemical sciences. He held a postdoc position at the University of California, Santa Barbara. He returned to Israel for an internship at the Weizmann Institute, and afterwards he has joined the Department of Natural Sciences with the Open University of Israel. Igor, please.
Gil, if I may add, Igor was the president of IVS before my term, and he did a fantastic job on it. So we have to acknowledge his contribution to where IVS is today is thanks to him.
Thank you very much. Thank you very much, Daniel. And so do you see my screen?
Yes.
Okay. So the topic of my talk today is kinetics of ammonia desorption and diffusion on platinum and its implications for the Ostwald process. And this is a joint work with my colleagues from University of Göttingen. So what we are really talking here, and let's look at these two important processes, industrial processes that literally put food on our table. And we're talking about Haber-Bosch, which is about fixation of nitrogen, producing ammonia, and perhaps less known subsequent process called Ostwald process, where ammonia is converted to nitrate fertilizers, while the key reaction behind this process is oxidation of ammonia by oxygen over platinum catalyst to produce nitrogen oxide. It can also yield to undesired side products such as N2, which reduces the efficiency of the process, and also N2O, which is quite harmful since it has greenhouse effect and also leads to ozone depletion. Now, what actually happens in this process, let's try to look at some microscopic steps which are happening during this reaction. The ammonia molecule lands on the majority terrace sites. Then, in order to react with oxygen, it must diffuse to the low coordinated active step site where it reacts with oxygen atoms. And along the way, it can also desorb and simply not reach the active site. So it means that we have to know in as quantitative way as possible about the competition between desorption and diffusion, and also about the equilibrium between adsorption on step and terrace sites, because then we can say something meaningful about reaction probability. So unfortunately, despite the importance of these kinetic processes, the details of Oslo process are still poorly understood. For example, the competition between ammonia desorption and diffusion platinum has never been investigated. In fact, even such a basic parameter, such a binding energy of ammonia at platinum 111, flat platinum 111 surface, there is no experimental consensus about it. In fact, the reported values are ranging vastly. The reported values range between 0.68 to 1.1 EV, and you can imagine that such differences can change the kinetic picture completely. Beyond that, real catalysts exhibit often, and always actually, diversity of active sites, steps, kinks, and so on. However, there are no reports in literature of site-specific binding energies of ammonia on platinum. And due to this lack of reliable quantitative information, we are often forced to rely on so-called surrogate empirically optimized models, sometimes even with unphysical parameters optimized for certain range of interest. And since they are not relying on fundamental elementary kinetic processes, they very often lack universality and transferability. And this is quite unfortunate because it was already Ostwald in his Nobel lecture in 1909 who actually said that, well, without understanding detailed elementary kinetics, our chances to understand this catalytic process in predictive way are very small. So how do we address such a process, and how do we understand, or trying at least to start to understand these elementary kinetic steps? A good starting point is to look at something which is even more basic than reaction of ammonia with oxygen platinum catalyst, to look at ammonia desorption. So seemingly simple experiment, right? So what is actually our fundamental observable in such experiment? If we do some very simple dimensionality analysis of this first order process, we see that this is the rate of appearance of ammonia in the gas phase. This is a depletion of ammonia adsorbate. So this is a first order rate constant. And this is the surface density of the adsorbate, which means that what we need to detect is the flux of molecules, basically the number of molecules per unit area, per unit time. So what we usually detect in most of experiments is density. And this can actually lead to significant deviations. So the method we are using here, the so-called VRK, velocity resolved kinetics. Briefly, the ammonia molecules produced in the molecular beam land on the surface, then they desorb, and then they detect it using multiphoton non-resonant ionization, which is a universal mean of detection. Then a pulse of electric field is applied here, and these ions are flying in the field-free region in this time of flight mass spectrometer. And then they also preserve their velocity component in the direction perpendicular to the surface, okay? Now they hit this detector, this MCP detector, followed by phosphor screen and CCD, overall can be taken as this ion camera, at position which is proportional to their velocity in the direction perpendicular to the surface. So by recording an ion image, we can actually record velocity or even velocity distribution. So this provides us a great deal of information because having velocity, we can convert density that we detect to a flux. We can furthermore decouple surface residence time from flight time to the detector, because this is a prerequisite to having a reliable kinetic trace. And once we have velocity distribution, we can deduce thermal sticking coefficient using principle of Dielectric balance. Now, if we will vary the delay between the molecule's dosing pulse and the ionizing laser pulse, we can detect a kinetic trace, which is time-resolved desorption flux. And this is how this time-resolved desorption fluxes look in real life. So what we are doing in this experiment, we are using two surfaces. One of them is platinum 332, highly stepped surface with 16.7 monolayer of steps. We use platinum 111, which is in ideal case, of course, is absolutely flat. In this realistic case, the density of steps is 0.004 monolayers. And this is what we are seeing in this kinetic trace. First of all, this sharp feature in the beginning, this is direct scattering of ammonia. So ammonia that hits the surface and bounces back in a single bounce collision. And this produces very narrow angular distribution at specular angle with respect to the incident beam, independent on surface temperature, but we are not after that. We are actually after the slow component. The slow component, the slow part, this long trace, corresponds to desorption. And that's what we see. We see that in the case of platinum-111, the desorption trace is bi-exponential, while in the case of platinum-332, the decay is single exponential, okay? So this is what the time-resolved kinetic trace, time-resolved desorption tells us. So we can try to model this with a fairly straightforward kinetic model, considering the following elementary processes. First of all, it's hopping between adjust and terrace sites, hopping from terrace to step sites and vice versa, desorption from terraces and desorption from steps. Now, while doing this feat, we are getting some kinetic parameters, which already teach us a lot, right? In the form of Arrhenius equation, this is the log of the prefactor, and these are the activation energies. So first of all, we learn that the fast component belongs to terrace desorption. Basically, what happens when the molecules are landing on these platinum-111 surfaces, where the steps are very sparse, since the distance they have to pass between the steps are actually 250 rows of platinum atoms, they can easily desorb along the way without reaching the steps. That's one thing. Now, the slow component, right? The slow component is related to the ammonia molecules that reach the steps and desorbed either directly from the steps or after hopping back to the terrace, because the steps apparently are stabilized in comparison to the terraces by 0.23 eV. What is actually quite remarkable here, and this is, by the way, the reason why we are seeing this by exponential decay, that the hopping barrier is nearly equivalent to the desorption barrier, 0.73 eV versus 1.1 EV for the case of desorption, which means the hopping is very slow. Now, moreover, what is again remarkable here, that the prefactor for desorption from the steps and the prefactor for desorption from terraces are nearly identical. And we know that in this Arrhenius equation, the prefactor is associated with entropy, which means that both on the steps and on the terraces, this connection of the binding of ammonia to the binding site is very localized. In fact, ammonia sits with its lone electron pair on top sides. This is the most stable site where ammonia binds to the surface. Now we can go one step further and we can say, okay, let's analyze this with the help of transition state theory, not just doing empirical Arrhenius equation. Because usually, you know, when you have moderate quality data, we are after binding energies and, you know, getting some empirical prefactor saying is something around 10 to the power of 13, but you don't have to do it when we have a high quality data, which can be actually quite sensitive. And then the prefactor is sensitive to the type of interaction the molecule experiences, because what we have in this expression is, of course, the recrossing factor to correct for crossing back through the transition state plane. And this we know because we know the sticking coefficient from the experiment. We can put the transition state, because this is a barrierless adsorption, actually here, and then the partition function for transition state, it's simply partition function of the gas phase. And then the partition function of the adsorbate becomes extremely sensitive to the kind of interaction. So we also know from DFT calculations for the system that the degrees of freedom, such as frustrated rotation or hindered translation, which is a molecule surface stretch, are closely coupled to the diffusion coordinate, to motion parallel to the surface. And therefore, in fact, we can only satisfactorily fit our data when we construct the adsorbate partition function such that it includes coupling of frustrated rotation and hindered translation to the diffusion coordinate. And pictorially, we can picture it like this. The molecule, the bond stretches, the molecular symmetry axis tilts, and then we are going to the next binding site, which is pretty much like sort of a pile walk, from one highly localized bonding top site to another with transition state allocated to the bridge site along this minimum energy path. So again, now we're getting really the desorption barrier and hopping barrier, and not only activation energy, because if we are doing this purely in a Arrhenius form, then we actually have a free energy of activation, which also includes entropic influence. Here we are able to disentangle the energetic and entropic influence by applying transition state theory, but the qualitatively and so quantitatively, the main take-home message remains the same. The hopping barrier is very high compared to the desorption barrier. This is actually quite unusual if we take into account oftenly cited in literature 12% rule, which states and often applied that there is a so-called universal empirical relationship between barrier of desorption and barrier for hopping. In fact, we see that ammonia platinum system is clearly an outlier due to this highly localized bond stemming from the connection of lone electron pair of ammonia to the top side. Now, further, what we can do, we can look at. Yes.
Igor, we need to wrap up soon.
That's exactly what I'm going to do. It's last slide. Yes. So, right. So at realistic conditions, obviously, the probability to reach the step is defined by the density of step sites and, of course, by the range of temperatures. So we are taking the characteristic step densities and temperature range of Ostwald process, and what we see using this desorption diffusion model, that in the characteristic range of conditions, actually, not all molecules are landing in majority terrace sites are able to reach the step prior to their desorption. In fact, ammonia must adsorb on or very close to step site in order to react, and this is not happening under typical Ostwald condition. Furthermore, under catalytically relevant conditions, other adsorbates like NO or O will be present on the catalyst and will likely decrease mobility of ammonia. And this, of course, calls into question to this so-called mean field approximation, which is commonly used in the optimized surrogate optimized model to model the Ostwald process, because the process may be, in fact, diffusion limited. To conclude, we measured desorption of ammonia from platinum-111 and platinum-332 surface using velocity resolved kinetics, and found precise expressions for rate constants for desorption from terraces, desorption from steps, and also site-to-site hopping at terraces, and site-to-site hopping from steps to terraces and vice versa. Here are the key parameters derived from this study. And we found that ammonia diffusion on platinum-111 must pass over a large barrier, which is in fact 65% of its binding energy, which is an exception to so-called 12% rule. And in temperature range typical for Ostwald processes, ammonia hopping rate is close to its desorption rate, which indicates that ammonia landing at the terrace can desorb prior to reaching the step. Therefore, the mean field approximation is questionable, since the process is likely to be diffusion limited. And this is probably the most important take-home message from this study. With that, I would like to acknowledge my colleagues in Göttingen, would like to acknowledge the funding, and to thank you for your kind attention.
Thank you very much, Igor. We are really behind schedule, so one quick questions will be great. Okay, so if not, we'll move forward. Thank you very much again, Professor Achino.
Thank you.
And our next speaker is Itzhak Buchin. I hope I pronounce it right. Itzhak got his bachelor in biophysics from Bar-Ilan University and his master in chemistry also from Bar-Ilan University, and now he's a PhD student in the Weizmann Institute, Molecular Chemistry and Material Science, in the lab of Professor Michal Neskes. Okay, please go ahead, Itzhak.
All right, thank you for the introduction. I'll try to be short and sweet. Thank you everyone for coming. My name is Isaac, and today I have the delight in sharing you sharing with you a collaborative effort between myself, Dr. Irit Goldian, and Dr. Sydney Cohen of the Weizmann Institute of Science, under the guidance of my advisor, Professor David Kahn. And today I'll be sharing with you our research on how humidity influences the mechanical behavior of halide perovskite. So halide perovskite with the chemical formula ABX3, a material I believe most of us are familiar with. The part of the reasons why halide perovskites as material have researched back onto the scene is because they pair a unique and very interesting set of properties in one material. The fact that we're able to produce high quality semiconductors via low temperature fabrication methods, being able to tune the band gap and being able to achieve high photovoltaic efficiencies are great within themselves, but being able to pair all of these materials and to collect them in a soft material is really what sets these materials apart. Because on the one hand, we do have already high quality inorganic semiconductors such as silicon and gallium arsenide. And on the other hand, on the other spectrum of semiconductors, we have organic semiconductors, which are very, very flexible and pliable. And halide perovskites sit very nicely in the middle, sort of in order of magnitude less in the mechanical properties for classic inorganic semiconductors, and an order of magnitude greater than the organics. So mechanical information on these materials is really integral for the future of these materials to be included in flexible photodetectors, flexible solar cells, and flexible LEDs. So the research that I'll be sharing with you today will highlight a gap in this knowledge, and we hope to fill this gap of knowledge. So before I move further into our research, I just want to clearly define the terms that I'll be discussing today: hardness and elastic modulus, both mechanical properties that are measured in gigapascals. So hardness measures the material's resistance to plastic deformation or permanent deformation, whereas the elastic modulus measures the material's resistance to elastic deformation or reversible deformation. And the best way that we can intuit what's going on the molecular level with these properties that I'll be discussing today is that hardness is the breaking of bonds, while the elastic modulus we can sort of understand as the stiffness of bonds. And just to give you background on what was discovered already about the mechanical properties of these materials, these two groups publishing around the same time provided similar results. And what they concluded was that predominantly the mechanical properties for these materials resides within the lead halide bond. There's a secondary influence from the A site cation, depending on on the size of the A site cation and also the degree to which the A site cation can participate in hydrogen bonding. The A site cation can change the lattice parameters ever so slightly of the unit cell, which then changes the length of the lead halide bond, which then changes the mechanical properties for these materials. So our objectives in our research was to measure the relative humidity, the effect rather of relative humidity on the hardness and the elastic modulus of halide perovskite single crystals. It was important to us to describe how the A site cation and how the X site anion affect humidity dependent mechanical properties. And we also hoped to elucidate how the presence of water in the ambient alters the mechanical properties of halide perovskite single crystals. So to achieve this, I synthesized 5 crystals that we divide up into 2 subsets. We have the methylammonium lead halide set, by where we change the X site anion or the halide that we incorporate into the crystal. And then the second set is the A site cation set, by where we change the A site cation and we keep lead and bromide the same throughout. And the instrumentation that we use for these measurements were humidity controlled nanoindentation, as well as some AFM techniques. Now, due to brevity of time, I won't be able to go into all the results, but I will be sharing with you today the hardness measurements from the AFM techniques and the results for the elastic modulus for the nanoindentation measurements. And just to clarify how we perform these measurements, we take a crystal we place it in the instrument of choice. We bring the crystal to a dry environment. We let it acclimate. We measure the crystal. We then increase to the humid environment. We let the crystal acclimate for 30 minutes. We measure on the same crystal in the same region. And then we repeat the process, but we go back to the dry setting. And on the same crystal and the same area, we measure the mechanical properties. So what we see here, as we go from low humidity to high humidity and back to low humidity, we see that the elastic modulus increases with humidity and subsequently decreases when we return back to the dry state. Now, for the A-site cation set, when we look at methylammonium and formamidinium, we see that formamidinium has the strongest response. And this was actually surprising because formamidinium actually has weaker hydrogen bonding than methylammonium. So this was quite peculiar, and I'll explain in a second why we think this is. And cesium lead bromide we see doesn't really have a significant change in its elastic modulus as we go from dry to the humid environment. It's within a standard deviation. And when we look at the X-site anion, we see the trend stays consistent as we go from low humidity to high humidity and back down to low humidity. The elastic modulus increases and is also reversible. And when we look across the entire set of these crystals, we see that as the size of the halide increases, the phenomenon diminishes, which is also surprising because we originally hypothesized that if the halide that we use is larger, then it would be able to participate in hydrogen bonding more, which would increase the phenomenon, but we see that this isn't the case. So these combined results had us scratching our heads a bit. But after a fruitful conversation with Anat Yitzhak of our lab and Professor Ilya Gruberg in the Bar-Ilan University, what we found was the following, and that is that the elastic modulus in both cases, in both sets of crystals, trends inversely with the empty space of the unit cell. So in blue, as you can see for the X-site anion, when the empty space increases, the response in the elastic modulus to humidity decreases. And I would just like to take a moment to define what I mean by empty space. I define the term empty space as the estimated total volume of the unit cell minus the volume of the ions within the unit cell, assuming that they are spheres. So this trend that we found across all crystals perhaps give us insight as to how intercalating H2O molecules results in a higher elastic modulus. So this is just for illustration purposes because halide perovskite isn't as ionic as these golf balls present it to be. I just want to illustrate the point that there are these cavities, there are these sort of empty spaces where the water molecules can intercalate into. And overall, the material becomes more tightly packed, more dense, which makes the material more stiff, which we measure as a higher elastic modulus. And so when we look at the hardness measurements, we see the opposite trend between humidity and hardness. As we go from low humidity or the dry state to the humid state and back to the low state, one, we see that it is reversible, but we see that the hardness actually decreases when we increase the humidity. And this was consistent throughout the hybrid organic, inorganic halide perovskite crystals. There was one exception where with the iodide crystal, we do see that it drops, but it doesn't return completely to where it was previously. So we think that this is due to material degradation. Again, the cesium lead bromide, the completely inorganic halide perovskite crystal, didn't experience significant change in its hardness when we changed the humidity. So taking a look at the trends from the hardness measurements, we find the following correlations. There is a weak correlation between the polarizability of the X-site anion and the change in hardness that the crystal experiences. And there's a stronger correlation between the hydrogen bonding strength of the A-site cation and how and to what extent the hardness of these materials change. So a possible explanation as to how polarizability and hydrogen bonding strength could affect the mechanical properties of these materials. When no water is present inside the material, the lead and the X-site anion have the greatest overlap. But when water intercalates into the material and forms hydrogen bonding with the X-site anion, electron density from the lead X-site anion bond is drawn away. The bond becomes weaker and is thus easier to break, which we measure as lower hardness. And for the A side cation, the stronger the interaction between the water molecule and the A side cation, the more the water molecule, the hydrogen bonding between the A side cation and the water molecule would draw the A side cation out of its ideal mechanical position for mechanical integrity, thus weakening. So the stronger the interaction, the more the integrity of the structure is weakened. So it's easier to break, which we see as, which we measure as a lower hardness. So overall, this research shows that the elastic modulus trends inversely with the empty space of the unit cell, and the hardness trends directly, but weakly with the polarizability of the halide chosen for the crystal, and strongly with the hydrogen bonding strength of the A site cation. Are there any questions at this time? And if we have time, I'd love to take some.
Okay, Yitzhak, thank you very much. We don't have time for questions, but still a short one.
Can I ask a question?
Please, Iris.
A very quick one.
Yeah.
Thank you for the presentation. The hydride phases of perovskite with water are well known. And I assume that you might have some of these on the surface of your single crystals. Have you measured the water intake and losses of your crystals? That's one question. And that would coordinate with my other question, which would be, have you tried to correlate your results with the density of your crystals? Because the density with different, at least with X halides ions, would be very different. In some cases, even the crystalline structure would be different.
Mm-hmm. Okay, so if I understood your questions, the first is, were we able to measure I guess the presence of water either on the surface or in the bulk, and then also were we able to detect any change in the density in these crystals? Yeah.
The second question was actually, did you correlate the changes in hardness and elastic modulus with the original density of the perovskite?
Okay, so okay, fine. So to answer your first question, we have an ongoing we have an ongoing question where we're still trying to have direct evidence for water inside the crystal. We have had some TGA mass spec results that have shown that that water is embedded deep into the crystal, but these results are have been difficult to reproduce. So the weight percentage for the weight percentage of water that perhaps leaves is on the order of magnitude of 0.02 weight percent. So we haven't, so I think that answers your first question. As for correlating the changes in density to hardness, because the amount of water that we think is entering into the crystals is so small, we're right now focusing on just being able to detect water and quantify the amount of water inside one crystal. We haven't yet been able to expand that specific question and that method to all the crystals. So we do hope that we would be able to expand it and be able to correlate it and to really show strongly that, you know, the more the crystal is able to uptake water, that you know, correlates very nicely with the changes, but we haven't gotten to there yet, but we do hope to get there.
Okay, thank you very much again, Yitzhak.
Thank you.
And our next big thing on the session is now our roundtable discussion. The topic of the roundtable discussion is energy challenges that we face today, the Israeli corner. Our moderator is Professor Doron Orbach, and we are also happy to have as a panel member Professor Emmanuel Peled. I don't have to introduce neither one of them, but I'll do it anyway. So Professor Orbach is the professor in the Department of Chemistry, the director of the Energy Center at the Bar-Ilan University Institute of Nanotechnology and Advanced Materials, and the leader of the Israel National Research Center for Electrochemical Propulsion, which includes 26 research groups from 7 leading academic institutions. Professor Orbach is a leading electrochemist and a physical chemist who heads a prolific research group working on frontiers topics in electrochemical, surface and material sciences. And on the practical side, Professor Orbach and his group work systematically on R&D of a wide variety of power sources, electrically conducting polymers, and water desalination.
חליק, בואו, אז צריכים להתחיל, עזוב, נו.
רגע, אז I'll say also one word about Professor Emmanuel Pellet, who is also here.
More words.
More words.
Stop with me and more words with Emmanuel. Not one.
Okay, so I guess everybody know Professor Emmanuel Pellet, so I guess. And anyway, Doron, I ask, let's do the discussion until 12:25. Then we have 4 minutes for flash.
אתה מתפרץ לדלת פתוחה.
Okay, thank you.
במקום אחר, הכל יתארך. יאללה, באיזה שפה? We do it in English?
Please.
Sorry, you cannot end at 12:25. At 12:20, there is the joint session of everybody in there. I apologize, that's the maximum you can do, and people are skipping the flash talks with this. So the 12:20 is really the maximum deadline.
But 12:30, we have the posters.
No, we have the 12:25, the explanation on the posters. There are the exhibitors talks also. We cannot miss that one. I'm sorry, Gil.
Okay.
Okay, so 12:20 is the last deadline. Apologize for that.
Good for me.
Okay.
Okay.
Good for me. So just let me just tell you that about Emmanuel Pellet, that about 2 years ago, Nobel Prize in chemistry was awarded to people who, in fact, led the community of lithium batteries, lithium-ion battery technology. So I believe that if 5 people would receive, would be able to receive Nobel Prize, Emmanuel would be included. So Emmanuel is one of the pioneers of lithium battery technology. So let's start the panel. Let's start the panels. This is a session in electrochemistry and catalysis, energy and catalysis. There is one question that I want to raise about maybe we have, in fact, let's face the most important challenge, which is a large energy storage. If you want to electrify a country like Israel, and we want to cover the country with solar panels, this is the only way to really reduce the use in fossil fuels. Then we need storage. And the question is, so solar panels now are very cheap, and we have here a great development in terms of cost effectiveness. We are facing a very severe problem of energy storage and conversion. And the question is how we do it. Now, let's remember, in Israel, we cannot use hydroelectric systems. Also, to compress gas, if people who knows the geology of Israel, we don't have options to compress gas deep in the earth. We have to go to electrochemical solutions. So we have, we can talk in terms of 3 economies. We have hydrogen economy, lithium economy, and the sodium economy for energy storage and conversion. So there is one, so I want to raise a question about the hydrogen economy. When we talk about hydrogen economy, of course, we want to produce green hydrogen. Green hydrogen is a green fuel, no carbon signature. And the question is catalysis versus electrochemistry. I want to raise a question. There is a lot of work of water splitting by nanoparticles. There's a nanotechnology for water splitting by we apply solar radiation to some nanoparticles, and then you may have a water splitting by sun radiation with some type of with some materials. And in turn, we have a classical electrochemistry that can work for us. Simply put electrodes with electrocatalysis, and it can be even moderate electrocatalysis, and then we can produce hydrogen electrochemically, and not by let's say by photochemistry. So the question is if we can really vote, for electrochemistry in producing green hydrogen. And then there is another question: when we have hydrogen, how we use hydrogen? So producing hydrogen, of course, is one of the options to use solar energy. And then instead of conveying electric power or lines by using chemistry, by using hydrogen, we can transport energy chemically more effectively. So there is a question how we use hydrogen then. So the question, if people want to answer or to have comments on my question. So a question here about hydrogen economy, first of all, about the production of hydrogen, electrochemistry versus photochemistry, and then how we use hydrogen properly. There is an option to use it in fuel cells. There is an option to use it in maybe in gas turbines, simply to use hydrogen as a fuel in turbines that can produce electricity from turbines. So this is a question that I raise, and it's very important. Emmanuel, what is your opinion?
Okay. Good afternoon or noon or morning to all of you. Well, I think that the hydrogen economy is not practical in Israel, because in Israel you have, in hydrogen economy, you need to have very large underground storage. You have this kind of storage in Europe and in the USA, but you don't have in Israel. Sometimes you need empty oil fields or rock caves, but we don't have it. So what we can do is we can develop catalyst for this reaction and not the system itself, like catalyst for hydrogen oxidation or evolution, and oxygen evolution for electrolyzers. This, I think, what we should do here.
Emmanuel, you are a fuel cell developer, and you demonstrate, I think, very impressive results on direct fuel cells. If you think about large energy storage, to what extent fuel cells is an option? If you think that you have fuel cells where each cell provides something less than 1 volt, and you have to connect maybe thousands of fuel cells in order to have, let's say, come up to high voltage. And you think about manifolds of hydrogen piping that has to connect fuel cells. So what is your opinion about use of fuel cells for large energy storage?
Well, you can use hydrogen either in fuel cells or in some gas turbine. And the question, what is the highest efficiency? So in order to get high efficiency in gas turbine, you need to work at quite high temperature. So I'm not familiar with this technology. I think that so far, fuel cells efficiency is larger.
Dear friends, we have to, the discussion just started, but unfortunately Daniel is very harsh and strict with the time that we have. So I would like to thank you again, Doron and Emmanuel, but we have to...
For the thorough discussions.
Sorry about that. And we have to do...
It's good for me. I have a lot of things to do. So it's,
No, actually, I heard you very carefully in the morning, and I was looking forward for this discussion. But we're out of time.
Just let me the last sentence. I want to just to close. We face here a very severe challenge, and and we have to think carefully. And I think we really have to join forces, working together on a very serious problem. The issue of of electrifying a country or electrifying country with green energy and large energy storage and conversion, it's a very serious. It's a big challenge, and it deserves discussion. And Israel can contribute a lot. Israel has good science, good scientific systems that can really help and pioneer finding solutions for these challenges. So Israel can contribute a lot to this critically important area.
Okay, thank you very much again. So now to our flash talkers. Guy, are we here?
Yes, I'm here.
Okay, Guy, you don't have 1 minute. You have about.
There's no. We need to go
seconds.
to the joint session, Gil. There's no time for flash. I thought the flash talks happened anyway behind your scene. The flash talks did happen on the other link. You don't have flash talks to do. Everybody, please join the plenary session. Sorry, Doron, it was a very short.
Well, it's good for me. I have things to do, so it's. Thank you very much.
Thank you very much, everybody. Thank you very much.
In the introduction, so we heard from this. Toda rabah. Thank you.
Goodbye.
Toda rabah. See you all.